All right, so we're going to draw the Lewis structure for the molecule. We're going to determine the total number of electron groups around the central atom. And then we're going to determine the number of bonding groups and the number of lone pairs, and then determine the electron geometry and molecular geometry. Got some molecules that we haven't worked with before. That's a ClNO, so I don't even know what that would be called, to be honest. Chlorine, nitrogen, oxygen. So that would be the skeletal structure. How many valence electrons do we have total?
18.
He was ready. 18 valence electrons. I was going to have to add it up. I haven't counted them yet. So 18 electrons, and when we're placing these lone pairs, right, we should subtract out the bonding pairs. So I've used up 4 of those for bonding. So that leaves us with 14 left. Always start with the most electronegative atom first, because it's probably going to end up with all those lone pairs in the end anyway. And so you can save yourself some time. So what's the most electronegative atom in this molecule? Yes, it is chlorine. If you're using the periodic table to figure it out, fluorine's the most electronegative, so whatever's closest. Chlorine, slightly more than oxygen electronegativity. So that's 2, 4, 6. And then we'll move over to the other terminal atom, 2, 4, 6. So 12 used, and we can place another lone pair on the nitrogen. Now the nitrogen doesn't have enough electrons. Only 6 valence electrons.
Would we pull it from the oxygen?
Yeah, double bond, and we'll pull it from the oxygen. So pull it from the less electronegative atom. It's going to be more likely to share.
No, I'm thinking out loud. Making me sound weird here.
And is that the Lewis structure?
No, it'd be like more at an angle.
Okay, so you're right that it would be more at an angle. For Lewis structures, though, doesn't matter. So the way you draw your Lewis structure is just to figure out the number of electron groups and bonding groups on your central atom.
Okay, so you don't have to do all the angles and stuff.
The angles don't have to be correct there. If you're trying to like draw a 3D representation of the model, then you'd want to incorporate those. Yeah, and I think that's one of the things that a lot of people get wrong is they see a Lewis structure and they think that's accurate. But we don't know what it's supposed to be until we've drawn the Lewis structure. So unless you know beforehand, which I do sometimes when I'm drawing Lewis structures, you're not going to know that this is supposed to be a certain angle. So let's use this AX notation, right? So we've got AX, E. How many X would be our bonding groups? How many bonding groups are there? 2. So double bonds even count as a single bonding group. How many electron groups or lone pairs? Just 1. So write the 1 in there. Usually leave 1s off. Right, so it's just AX2E.
So that would be the VSEPR formula?
So you could take that up to this table probably, yeah. So electron groups is going to be your bonding groups plus your lone pairs. A is the number of bonding, not A. X is the number of bonding groups, E is the number of lone pairs. So we're looking for total electron groups of 3, and then 2 bonding groups, 2 lone pairs. So our electron geometry is going to be trigonal planar. And now the electron geometry is including those electrons as a group there. If we're talking about molecular geometry, then it's just going to be bent. And hopefully after Monday, so we can, I'll draw this so it has those angles. Hopefully after Monday, it's a little bit easier to do this without having to use a chart, having done all of these. Yeah, so it's bent. What's that bond angle going to be? First, what's the ideal bond angle? 120. So we got 3 groups. You take a circle and divide into thirds. You got 120 degrees each. Octahedrals, all 90s. Okay, so 120 would be like ideal bond angles. And then we're talking about bond angles here. Really, it's going to be like the notation that they used that we had on Monday was if I'm going from the chlorine, nitrogen, oxygen bond angle. So that would be tracing, what should I do with the highlighter? So we're looking at the angle, that angle. What is that actual angle going to be?
Like more than 90?
It would be more than 90. but less than 120. So usually we'll use whatever the ideal angle is. Say it's going to be either it'll be exactly that, or it'll be less than. Here, because we have this lone pair, that lone pair is providing a lot of repulsion because it's pure electrons. And so this bond angle is going to be less than, still in the red, less than 120 degrees. What was it? 116.2?
Yeah. Exact.
Yeah, if you want to if you want to figure out what the exact bond angle is, you'd have to measure it somehow. I don't know how you would do that. Again, I queued this up because it's going to come up a lot today. Quantum physics. So why is it exactly 116 point whatever? Quantum physics, we're not going to talk about it. So we'll keep coming back to that. Is everybody good on this one? Okay. So I3 minus iodine. 7 times 3. Yeah, so 21. Yep, 21 electrons from just the iodines. And then we add 1 electron because we got a negative charge. So 22 total electrons. And we used 4 for bonds. So it gives us 18. And then we can place our remaining electrons. 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10, 12, 14, 16, 18. Did a bad job of counting. I always end up skipping something when I'm counting by twos. Please verify. Yeah, did I 2, 4, 6, 8, 10, 12? Is this 20?
No, that's 18.
That's 18. Oh, this is 20. Oh, so it did count it right the first time.
To add, or we have to give 2 more. Was it giving 2 more to the central?
Give 2 more to the central atom. Yeah, if you're getting extras, they go to the central atom. Okay. So how do we predict the molecular geometry?
It has 1, 2, 3, 4, 5 bonding. There's 5 bonding.
5 bonding?
I thought there's only 2.
There's 2 bonding, 3, 3.
There's
AX2, E3.
Yeah.
Yeah.
Yeah, AX2, E3. You're thinking about you're thinking about electron groups.
Yeah.
Yeah, total electron groups is 5.
Would it be the linear? It's that. Yeah, it's the linear one with the 3 on the equatorial.
Yes.
Wait, why would it be 5 bond? Oh, because of bonding groups and then the lone pairs.
Not 5 bonding, but 5 electron groups.
My bad.
Yeah.
Because
Yeah.
it'd be the 3 lone pairs and then the 2 bonding pairs.
Yeah, so we saw it in this orientation a lot. And then an iodine up here, iodine down here. Yeah.
Are lone pairs only coming from the central?
Yes.
Okay.
Yeah, we're basing all of our geometries off the central atoms. And that does include if we have a molecule that's more than just, so we have a molecular or backbone, right? So if there's more atoms that could be considered central atoms, we could do geometries around those.
So would this one also be bent since they have the 2 or no?
So since these lone pairs are all essentially trigonal planar, so if I was to look at, so if I draw like an eyeball, so if we're looking down this way, give that a pupil. That's creepy looking. So then we'd be looking at an iodine here, and then an iodine behind it, and then an iodine behind that. So we'd really only see one iodine, and then we'd see a lone pair, and a lone pair, and a lone pair, all split by 120 degrees evenly.
And then would it be polar or non-polar?
Is there a difference in electronegativity or a difference in charge on one side of the atom or the other? It's perfectly symmetrical.
So when it's not symmetrical, then it'd be polar.
If it's not symmetrical, then it might be polar.
Might be polar.
Yeah, and then you're going to look at, for something like this, if we replaced an iodine here with, I don't know, bromine, or actually no, let me go the other way. I was thinking iodine. So if we replace it with fluorine, now the fluorine is more electronegative than iodine, so this would probably be polar. Because the fluorine's the more electronegative side, would have a slightly negative charge, and then the iodine on the other side would be slightly positive. And so then our plane of asymmetry would be through the middle there.
Okay.
So if there's something that is asymmetrical about it, then you can say, okay, maybe it's polar, and then you look at either are there more electrons or lone pairs on one side or the other. I think the one that's similar to this, but has one fewer lone pair, is actually water. Actually, let me try and draw it like a similar orientation. So water would be this, but then these would be to the sides. So you got hydrogens. So it is one fewer electron group total. So it is a tetrahedral instead of a bipyramidal. And here you can see like the way I've drawn it here looks asymmetrical. So on the right side we've got two lone pairs. On the left side we've got two hydrogens. Those lone pairs are going to be more negative than the hydrogens. I can redraw this so that it's like this. This is doing some weird perspective stuff. So if we're looking down from the side of the lone pairs, and we've got the lone pairs on either side, and the hydrogens top and bottom. Now from this angle, this looks pretty much symmetrical, assuming that the hydrogens are going straight back. So for this, we put a bracket and a negative charge.
Oh, and then negative. Yeah, I forgot.
Yeah. Now it doesn't say it here, but what's the iodine to iodine bond angle? 180 degrees, because it's a line. So it's linear. Yeah, and it would be exactly 180 degrees. Did we look at? We didn't look at these like in lecture, but if you're drawing something into the board or into the page, it's got dashed lines. If it's a solid wedge, then it's coming out of the page. It's perspective.
So dash is like behind.
So it's like trying to think of an example that's not in a video game. But like in video games, a lot of things, if you're still able to know where it is and it goes behind something, then it's like either an outline or there's a dashed line to say I can't see this thing directly, but it's there. Yeah. Yeah.
Oh, like an object permanence. I learned about that in psychology.
Yeah.
Where you, like something's there even though you can't see it.
And so it's, yeah, that's
The
the
dashed.
part that you couldn't see behind the page. I don't know, aside from telling you this and saying if you want to get better with this, you need to practice looking at things like this. It takes practice to get used to seeing those. I'm not expecting you to be able to draw those. Like I was saying with larger molecules, here we've got multiple sort of quote unquote central atoms. The nitrogen, the carbon, and then this carbon, and then even this hydrogen over here. And we can predict the geometries of each of those individually using VSEPR theory. Okay, these are our interior atoms. And it's the hydrogen, oh, dang it, it's the oxygen. Literally just did it again. It's the oxygen and not the hydrogen. And so when we're doing this, we say we'll just isolate them. So if you've got your Lewis structure, we cut this off here if we're going to do nitrogen and say, okay, inside of that box, how many bonding groups do I have? Yep, so this would be AX3, and how many lone pairs? AX3E. And then if we're going to do carbon, then we just make another box, right? So we're only thinking about how many bonds carbon has and not considering the other stuff that's bonded to it. So for carbon, how many bonding groups?
What do you box both carbons though, or just one at a time?
Well, they're two different carbons. They've got different attachments.
Oh, okay.
Yeah, so it's not the fact that it's like the number of types of each atom, but for literally each individual atom that makes up, and that's why I said this is like a backbone, right? The backbone of this would be the nitrogen, carbon, and oxygen. The other atoms are all terminal, right? So they're not attached to anything else. So what would be our electron groups here for, yeah, AX4. Pick a different color. Now we do this other carbon, AX3. Because the double bond counts as one. Oh, we do this one.
So the carbon with the
Yeah, V2.
AX2, E2.
So you can only have four bonding groups?
In most things, especially, so this is an organic molecule. I actually think this is, what is it? It's an amino,
NH2,
it's an amino acid.
CH2,
I can't remember which amino acid it is. So then these are already actually over here. So for the nitrogen, 4 electron groups, 1 lone pair. It's going to be trigonal pyramidal. For the left carbon, it's going to be 4 electron group 0, so it's tetrahedral. And then the rightmost carbon, 3 electron groups, 0 lone pairs, so trigonal planar. And then for oxygen, it's 4 and 2, so that's bent. Yeah, so treat each central atom individually and then figure that out. You might be thinking, these groups are big, they might interact with each other, and they do. That's more organic chemistry. Their shapes are all going to be slightly different, and I don't expect you to even know how those are going to work out, right? So those bond angles changing a little bit depending on adjacent centers, how they rotate. Let's do another one of these. Predict the geometry about each interior atom in an acetic acid and make a sketch of the molecule. What are our centers here?
Would be a carbon, right?
One of the carbons, which one?
Or the middle one?
Definitely the middle one. What about the other carbon?
on the left.
That would be a central atom as well?
And then the oxygen, yeah, which one?
Just oxygen?
Yeah, the one on the right. So
Is that meant to like trick us? With, like,
Huh?
without having the bonds or?
it's another way that structures are written. So it's not necessarily to trick you, but it's could exist. Yeah.
Is this because of hydrogens only have one bond? Can only have one
Mhm.
bond to them, so there's no point in like
Yeah.
like condensing it?
So yeah, and another way, organic chemistry here. That's the same thing. So the end, if there's an end of a line, it's a carbon. If there's a corner in a line, that's also carbon. And then in organic chemistry, if you have a carbon like this is by itself, it's always going to have 3 hydrogens. So in organic chemistry, carbon always forms 4 bonds. Okay, so for our first center here, what's our, at AX, well, do we even have E?
Oh, AX2, right?
AX4,
AX4.
AX4.
So the H3
because the hydrogen they don't.
means
Oh,
3
so you're not
hydrogens.
taking that. Okay,
Yeah. So that one's AX4, and then the central carbon here, the middle one,
AX3.
AX3.
this last one's a little bit tricky, the oxygen.
It'd be 2, right? It'd be
AX2, but with an E. Two, yeah. I couldn't think about it
Yeah.
fast.
So there's double pairs counted as one X, right?
Double bond, yeah. Yeah, the double bond counts as 1x. So AX4 is what geometry? AX3? Trigonal planar. AX2E2,
That's bent.
bent.
That's Brent.
That's Brent. Oh, Brent.
Hershey Brent.
just hydrogen. Yeah.
Okay, now the trickier part. It says make a sketch of the molecule.
You gotta add 2 more lone pairs.
Okay, so to start with, now I feel like Bob Ross. Just draw some happy little bonds. Happy little carbon. Okay, so that part's going to be our flat part. So trigonal planar, is planar. So we draw the whole thing in line with the page. So if I've got my carbon double bond to oxygen, I can just put a bond here and a bond there. That's trigonal planar. We don't have to worry about any dashes or any wedges. And then we can attach our other central atoms onto there. Well, oxygen, and then the carbon over here. And then for, which one do you want to do? Doesn't really matter.
We'll do the carbon first, the one on the far.
Do the carbon, okay. There's two ways this can go. We can either have our, so we're gonna have one hydrogen that's gonna be in the plane, and the other two hydrogens are gonna be away from the plane, one in, one out, right? We wanna do about 109.5-ish. And that's a big ish. So it can either go that way or it could go down. And then either way, usually it's hard to explain why. So the one that goes straight down is usually the one that's in front. And then the other one is the one that goes back at an angle. Okay, so the AX2E2 bent, we can make the bond to the carbon and the hydrogen bond, those can be in the same plane. And then for AX2E2, what's like the base shape there for 4 electron groups? Tetrahedral. So it's a tetrahedral. So it's going to be the same thing that we did here with the carbon, with the 3 hydrogens. That's also a tetrahedral. But now 2 of those are going to be lone pairs. We'll do it like, nah, I don't like it. We're going to do the lone pairs just kind of like that. I think actually probably wouldn't even draw the lone pairs in, to be honest. But we can draw them in. You could like, I don't know. That's the idea though. So based on each of those individual carbon centers, we can actually make a prediction about what this molecule would actually look like. We haven't talked about it yet, but single bonds can spin. So like this CH3 would be just rotating. And this hydrogen over here could just be spinning. And then all spinning relative to each other. Just going. Okay, so this is a condensed, even more condensed than the previous structure that we saw. So what is the molecular geometry about nitrogen and CH3NH2? So it's AX3E. That's trigonal pyramidal. Diatomic molecules, polarity is all about the difference in electronegativity. We talked about this some. The real quick and easy way is to compare how far apart things are on the periodic table. More specifically, how many columns over they are. So something in a row or in a single column, there's going to be a difference in electronegativity between these. But if you're moving at angles here, it's almost more important that you're going left to right. So for something like chlorine and hydrogen, that's one of the easiest ones. Because how far apart on the periodic table are chlorine and hydrogen?
Very far.
They are very far.
Opposite sides. Where it starts to get a little less clear is if you get two things that are right next to each other, so like nitrogen and oxygen. Oxygen is more electronegative than nitrogen. How much? Definitely not as much as the difference between chlorine and hydrogen. If you're 2 things apart, so like carbon and oxygen, that's enough that you're probably going to have a polar covalent bond. Nitrogen and fluorine in anything is going to be polar covalent.
So fluorine and anything is polar.
Unless it's with itself. Fluorine and anything else is probably going to be polar covalent. Chlorine might give it a run for its money, but that's it. So in diatomics, it's just between these two, the bond polarity is what determines if it's polar or not. And there needs to be a difference in polarity. For molecules, we need to consider the shape along with polarity. So in something like carbon dioxide, we've got 2 equal carbon-oxygen double bonds. And because those are directly opposite each other, that electronegativity, even though that one of these bonds by itself would be polar covalent, we've got an identical polar covalent bond on the other side. So from the outside of this molecule as a whole, there's no dipole moment. There's no difference in one side compared to the other. So this would be a nonpolar molecule. Water has two polar bonds, but the thing about water here is that it's asymmetrical. So we did talk about this a little bit earlier, without even considering the fact that it makes hydrogen bonds. But we've got a bent molecule, and we know that there are lone pairs present on this side of the oxygen, right, opposite the hydrogen. So that side is going to be slightly negative. This side is going to be slightly positive. So draw its Lewis structure, determine its molecular geometry. And like I was saying earlier, if it's perfectly symmetrical, then it's not going to be polar. If there's asymmetry in it, like differences in bonded atoms, so if we use the example from before, if it's iodine and then like fluorine, now you've got an asymmetry there, and it's probably going to be polar because fluorine's involved. And then this is the way that the book says to do it. I think I cut the vector slides out. So how many of you guys are familiar with vectors and how to add vectors together? One. So vectors, I guess if we were to explain it simply, if I put a person here, and then I tied a rope to that person over to here, and then I pull this person that way, that would be like one vector. There's a force and it's going in that direction. Now, if I put another rope on this person, and then I pull that way with an equal amount of force, is the person going to move? No. Those vectors are equal, and they're exactly opposite of each other, so that force cancels out. Now, what if I take this, and instead of putting this person over here, I put them over here, and now they're pulling that way, same amount of force. Which way is that person going to move? Yeah. That's vector addition, essentially. So we've got a vector is specifically a force in a direction. You got speed and direction, which is also velocity. Velocity is a vector. Anyway, so yeah, so those are vectors. Now, for some of our molecules, they're going to be more complicated. So we could add a third rope here. So now if they're all pulling flat in the plane, draw that so they're a little more even in length. All right, so now we're pulling in 3 directions. Can I get the eraser, please? There we go. And I'll tell you that these are all 120 degrees. So is that person going to move? And if you went through and you did all the vector additions and you had numbers to plug in here, it would be 0. So it wouldn't move anywhere. So when we're talking about is something polar or not, and we can look at this molecule over here, now I've got fluorine, and the fluorine is pulling, and it's got a lot of magnitude. The iodine on this side, because it has the same electronegativity as the other iodine, it's got a lot less magnitude. And so our difference in electronegativities on one side of the atom or the other, or molecule or the other, depend on what's attached and how electronegative it is. So in this case, would that iodine move, so to speak?
Yeah.
Because the fluorine's pulling a lot harder than the other iodine. So our overall vector would be in that direction. So if you can draw vectors, they're pulling in a direction and not canceling each other out, then it's polar. The much easier way to do it, aside from a few exceptions, is if there are lone pairs on the central atom, and it's not this, what was it, AX2E3 is an exception, because we have lone pairs, but they're evenly spaced. That was actually the iodine. So since these lone pairs here are all evenly spaced out, then that's not going to be polar, even though there are lone pairs on the central atom. The other one is AX4E2, And that one's a little bit easier to see. That's square planar. So I put my molecules out here. And then I put a lone pair on top and the lone pair on bottom. So as long as all the other atoms are the same, those lone pairs cancel each other out. And all the other bonds will cancel each other out, so that's nonpolar. I believe those are the only two exceptions, though. Okay, so we have a molecule, contains 3 identical polar bonds in a trigonal planar molecular geometry. Is the molecule polar? Yeah, so this is that pulling in 3 separate directions. Trigonal planar is symmetrical, so no, it's not polar. The answer is almost, I don't know if I've ever seen the answer be unable to determine with the amount of information given. It's a trap. Oh yeah, here's some more vectors. Adding them together. So assuming that all of these are the same, like things like linear, trigonal planar, and tetrahedral will all be nonpolar. Trigonal pyramidal will be polar. Now they have it drawn here with the atoms there, but there's a lone pair on top also. And then bent will also be polar. And the easy shortcut, if there are, it actually did change this, good. If there are uneven lone pairs. So to keep using the same example, oh wait, I don't need this TV to show you this simulation. Hold up. Oh, let's go into the COS website. Just reload that was going to be the wrong simulation. Also, I don't know why this website sometimes it loads and it gives me the UPS logo for the website. Up at the top, like on the tab. It's supposed to have a different logo, but it's like, the internet is slow. I've been learning Japanese, yeah. So I can watch anime without subtitles. It's no joke. Okay, here we go. Bam, 3 lone pairs. So there it is in all its linear glory. The cool thing about the simulation too is that you can actually grab the individual molecules and try and make it do something else. And it always ends up going back to the same thing.
You take those balloon thingies?
Yeah.
You know what I'm talking about, the big ones?
So if we look at it this way, straight on that iodine, this was the angle I was trying to draw. These are evenly distributed lone pairs, right? And then if I even add another, oh actually wait, I gotta replace.
What would be the molecular geometry for that one, the original one?
That original one, molecular geometry would be linear.
Or
The electron geometry is bipyramidal.
bipyramidal?
Yeah. Trigonal bipyramidal technically, yeah.
Right.
And then this is the square planar. This will actually give you the electron geometry and the molecular geometry. So here, again, evenly distributed lone pairs. So is this polar or nonpolar?
Polar. I mean, non-polar.
Nonpolar. If I take one of these off, polar or nonpolar?
Non-polar still? Oh, no, polar is polar.
Polar. Unevenly distributed lone pairs.
Yeah.
Take another one off.
Polar.
That's weird.
Oh, there we go.
You know- I know.
Cody,
Did not intend.
this
What else can we go through here?
start laughing.
What happens if you just keep adding like?
You know what I know?
It only goes so far.
Oh, it only goes to.
Oh, here we go. I was trying to get something different. Polar or nonpolar?
It is.
Only one thing on his mind.
Oh man. I would say polar.
Yeah. It would be polar. Huh?
So is it uneven lone pairs?
Yes.
Okay.
So if they're, yeah.
So if it's like 1, 3, 5,
Well, 3,
4.
You have even lone pairs. Not bad.
that's 3 lone pairs. But this is what I mean by evenly distributed.
Yeah.
Yeah. Because even if I do this, that's 3, but they're now unevenly distributed. So you can look at them from some angle and they won't be evenly spread out.
It's not the uneven amount, but the distribution of them?
Yes. Yeah. So I don't mean even as in 2, 4, 6, 8.
Okay.
Okay, yeah, I was like.
Thank you.
so
Yeah.
what do you do?
Not symmetrically distributed. Okay, so that's the idea there. So aside from a few situations, easier to just say, are there lone pairs? So CF4. Do I need to go any further? So the only situation that you would have, is nonpolar. Okay, I'll let you do your own research, draw your own conclusions.
Non-polar.
Yes, sir. Thank you for your contribution. Is it not? Is it nonpolar? It's nonpolar. All right, molecular shape and polarity. I said I was going to dial it in. All right. Yeah, so these are magnetic marbles, actually. I keep meaning to buy these. I'm going to buy some, and then I can bring them to class and you can play with them. Yeah, so, well, why don't oil and water mix? Why does the oil always get pushed out of the water? Because it's nonpolar, okay. But it's more specifically because the water molecules are attracted to each other, kind of like the magnetic marbles are. So if there's a water molecule near a water molecule, and there's a hydrocarbon in the way, an oil molecule, it's going to push in or through or around the oil molecule to get to that water molecule. And so as the water molecules all try to stick together, and they'll try to get as close to each other as possible, they just end up pushing the oil molecules out of the way. So they end up getting squeezed out of, kind of like, it's not a great analogy. I was gonna say like a sponge. If you squeeze the sponge, it pushes all the water out of the sponge. Almost just really just by like physical action. And that's what's happening here. When you try to mix the oil in the water, you're forcing the oil into the water, and then the water squeezes it all out.
So pretty much water is racist? You think about it?
Polar molecules, yeah, I guess to nonpolar molecules a little bit.
Or I mean,
So the same thing would happen is if you had magnetic marbles and regular marbles, you could jumble them all up into a bucket or something, and if you just shake it for a little bit, all of the magnetic marbles will find each other and exclude the non-magnetic marbles. Because the marbles, they're magnetic, they have a dipole, north end, south end of the magnet. Now soap, it's the great equalizer, brings them all together. Soap has a polar end and a nonpolar end. So this is why you can't, because water is just not interested in nonpolar things. If you have oil or butter or grease on your hands, you can't get it off without soap, because the water will just run off of it. The soap molecules have a polar end that'll get caught in the water, and then they have a nonpolar end which gets caught in the grease. And so then there's a handle for the water to grab onto and remove the grease. Valence bond theory. So Lewis model is an oversimplification, which I think we knew. It's drawing everything flat. The angles don't really matter. They don't matter because it doesn't really do much, aside from provide us the tools to do VSEPR theory and apply that model. It's supposed to be like. So more advanced bonding theories will take quantum mechanics or quantum physics, which we're not talking about. They'll take those theories and apply them to the bonding. So modern quantitative approaches accurately predict many properties of molecules, such as bond length, strength, molecular geometries, dipole moments. Some of that is actually used in a project that's really cool, still going on, called Fold It. I think it's called Fold It Home now. And you could download this software, put it on your computer, and it's like, actually, the modern equivalent I think now is like crypto mining almost. But what they were doing is, if you weren't using your computer and it was just sitting on and idle, they would try and fold proteins using quantitative methods on your computer and figure out how proteins might fold, and then determine what like optimal foldings are for proteins, because that's what part of what makes the proteins work the way that they do. And so hundreds of thousands of people have this software on their computer, and while they're not using their computers, it's just brute force crunching the numbers to try and figure out how these proteins actually fold. And you can use that kind of thing to develop drugs for like HIV or other viruses, that kind of thing. We're not doing quantitative, we're doing qualitative, because we're not talking about quantum physics. Again, this meme is so applicable. Valence bond theory, the core of this, orbitals overlap as a chemical bond. So electrons reside in a quantum mechanical orbitals that are localized on individual atoms. They may be standard SP, D, and F atomic orbitals, or they can be hybridized atomic orbitals that blend two or more standard atomic orbitals. So that's what we're going to talk about today. Figuring out how they're hybridized is actually not that hard. So when two atoms approach each other, the electrons and the nucleus of one atom interact with those of another atom. And valence bond theory looks at those energy changes resulting from those interactions. And then if the energy of the system is lowered by the interaction, you get a bond. And actually, there's another simulation that I wanted to use here. See, now it's loading fast. That is what this is, atomic interactions. So this is, let's do one that's got a better, oh, not moving. Oh, neon, I see. So we've got on the left there, that's a pinned, what are we on, argon. And then I can move this argon. So as they get closer, or as it's far enough away, there's no interaction. So there's no favorable energy, that's zero energy. As I move it closer, that energy goes into this well and decreases until it reaches a minimum. So that's like the ideal bond length. If I go too close, then it goes up that curve to infinity and beyond. And if I let go, it bounces. So if you get close enough, you actually get this oscillation, and it'll keep bouncing back and forth in that energy region, which is actually what happens. So they don't like form like rigid bonds that stick together. They're actually constantly vibrating, and they'll be they do all kinds of stuff. So that's what this is talking about. Satisfying to watch. If I get it, oh wait, do this one. This is science. This is what science is. Okay. So those are our orbitals, and that's what this valence bond theory is. If we get to the right distance, there's a ideal overlap. There it is. All right, so as we get closer, we reach this ideal distance, and that ideal distance is where the ideal bond length is. You get too close, that energy is not beneficial. Get too far away, and it's not even interacting. The interaction energy is usually negative because that's stabilizing. If we can get into a lower energy state, we talked about how breaking bonds always requires energy to break bonds. Forming bonds always releases energy. So here we're taking two separate, and this one I think is hydrogen, taking two separate hydrogen atoms and bringing them together so it would release energy most of the time. It releases energy to become more stable. And then, yeah, commonly the electrons come from two half-filled orbitals, and that's primarily what we're going to talk about it as. In some cases, they can come from filled orbital overlapping with an empty orbital. Those are called coordinate covalent bonds. If you take Chem 2, we talk about them Chem 2. I think they're really interesting. So when they get close enough, they overlap with opposite spins, and they can stabilize each other. So to summarize, right, valence electrons, they reside in quantum mechanical orbitals. Again, they're not specific points, wave functions. The chemical bonds results from the overlap of two half-filled orbitals, and the electrons are then spin paired. So you get one with a plus 1/2, one with a minus 1/2. And then the geometry of the overlapping orbitals determines the shape of the molecule. Now, we're going to be using VSEPR theory, actually, So this is like the culmination, the combination of all of the things that we've covered so far in terms of drawing structures. We're going to use Lewis structure to figure out how many electron groups, how many bonding groups we have. And then we're going to use VSEPR theory to figure out what the shape is. And then we're going to use valence bond theory to figure out which orbitals are actually interacting. So here, this is actually one of the few things that actually works out this way. Exactly. So if we were to draw all of the orbitals out here, these are all p orbitals, right? So the red ones over here, p orbitals. There's 2 of them that look like, or there's 3 of them, sorry, that look like figure 8s. I'm just so bad at drawing right now. I drew 2 of the same one. All right, so those are the 3 p orbitals. Here they're all stacked on top of each other around the sulfur, and then the blue inside is the 1s, or is the s orbital. And so these hydrogens each have a single electron, and when they get close to the sulfur to form a bond, their single electrons can interact with some of the p orbitals on the sulfur to form new bonds that are lower in energy and therefore more stable and beneficial. And if we looked at this, I guess, before seeing this structure, you would probably say, oh, sulfur, hydrogen, that's going to be something like, it actually ends up being the same as water. And from that, we would say, oh, that's probably bent shape. It's probably about 109.5 for the angle. So that's the VSEPR theory prediction there. In reality, it does this, and it's a lot closer to 92 degrees. That's not always going to be the case. The cases that we're going to talk about and that I expect you to know are the ones that sort of follow the VSEPR theory more. But this is one example where you can see that VSEPR theory is not doing the greatest job. Because again, quantum physics. So what is a chemical bond? So what is a chemical bond according to valence bond theory? D? D, yeah, definitely not A. It's not just a lone electron pair. Those are lone pairs. It is actually B. Yep. So the overlap between half-filled atomic orbitals on atoms. So we had 2 atoms here, half-filled hydrogen, and then these half-filled orbitals in sulfur. All right, so again, doing this just like we did for sulfur is not always going to work out. So in that sulfur doesn't do very much, or I guess hydrogen sulfide. There's not a lot of, what we're going to learn is hybridization going on here. It's pretty much exactly the atomic orbitals overlapping without any change. And that's why we see this 90 degrees. In carbon, though, if we just think about carbon and hydrogen and how that forms bonds, most of the time it doesn't form just 2 bonds. But if we were to use just this half-filled method, we would see that carbon has only 2 lone electrons in its 2p orbital, 2 half-filled orbitals. And so from this, we might predict that, well, we can only bond 2 hydrogens. Because this half-filled needs to find a half-filled, and then we'd find another hydrogen that was half-filled. And so that would go there, and this would go here, and that would be the end of it. Reality, though, says it's this, which is far from the 90 degrees. So what's happening instead of just using these straight p orbitals, the straight atomic orbitals, is we get something called hybridization, where the orbitals shift in a way that actually becomes more energetically favorable when it interacts with other atoms or when it forms bonds. So they're still localized on atoms, but there are different shapes and energies than standard orbitals. So the standard p orbitals would be in, actually. Right, if we have the standard p orbitals, what shape would that be? What molecular geometry or electron geometry? Octahedral? So you got 1, 2, 3, 4, 5, 6 groups. So that was, let's just call it AX6. So this would be octahedral. So anything that would interact with only half-filled p orbitals should be, in theory, octahedral, or some derivative of octahedral. Instead, we see other things. Hybrid orbitals minimize the energy of the molecule by maximizing the orbital overlap in a bond. So it says if I can change my shape of this orbital, I can get better overlap and better coupling between those two electrons. And then your electron probability density is more concentrated in a single directional lobe. So the area where that electron is going to be more in between the two atoms that are actually forming a bond. And therefore also more shared. So why do atoms form bonds? Think electron configurations. Stable, yes. How many electrons do they want to have? 8. So if they can get 8, they're trying to share these electrons. If the carbon, if we go back up to here, if the carbon can change the shape of its orbitals to form these 4 bonds, and if it can move that electron so that it's more between the hydrogen and the carbon, instead of the traditional p orbital, so this would be a single p orbital. So according to this, 50% of its probability density is on the wrong side of the atom. So if the electron is spending time over there, then it's not being shared with the hydrogen. It's not spending time in between the two.
So would those two ones that aren't paired shrink down, and the ones that with the hydrogen get bigger?
Bingo. That's exactly what happens. So the side that's close to the hydrogen gets larger, and the side that's not gets smaller. And so it's actually hybridizing. Oh, I went too far. It's hybridizing with the s orbital, taking on some of that s character, in a sense, and combining it with the p character, p-shaped character. Here's where we were. And then this will only happen to the degree that the energy payback from the bond formation is large. So if that's a favorable bond to form, then you'll get more hybridization, like we see with the carbon, where we get almost exactly a tetrahedral, exactly 109.5. In the case of this hydrogen sulfide, the H2S, where we saw 90 degrees instead of any hybridization, that's because that bond, it's not favorable for the sulfur to hybridize any of its orbitals in order to form those two bonds. So if you had the information, if you had what the actual was versus whatever VSEPR is predicting or hybridization, you could actually make some sort of qualitative determination of how favorable the hybridization is, how close it is to those ideal ones. And we're going to simplify things, only focus on hybridization of interior atoms. And we're going to assume that the terminal atoms stay unhybridized and that we're just interacting from a distance. Okay, so the number of standard orbitals added together always equals the number of hybrid orbitals. And we're going to predict that hybridization using VSEPR theory. So for CH4, we would say that's a tetrahedral. We also know that this would be AX4. And it's actually this X4 that tells you what the hybridization is. And we can only hybridize orbitals that actually exist. So when we hybridize orbitals, there'll never be more than one s orbital. And we can have up to 3 orbitals that become part of that hybridization. So that's what we're seeing here. We've got 2s and 2p orbitals. When we hybridize those, they all become the same. So 4 orbitals, sp3. So how many? sp3 is also 4 orbitals. We're taking the s and adding it to the 3 p's. And then, I don't know if the meaning of degenerate has changed or something. in chemistry, what we're saying is that each of these orbitals has the same energy. So we take a bunch of things that used to have separate energy levels and they get combined, then they all have the same energy levels. That's what it means by that the orbitals are degenerate. So these are the shapes. And so you can see these are the regular orbitals, right, unhybridized. And then as JD pointed out, or guessed, the side that would be facing towards an individual bonded group is going to get larger and the other side gets smaller. So that electron will spend more time on the side of the bonded atom. And remember, you don't need to know that by combining these, we get tetrahedral, or that by combining these, like here we're combining one s with three p's, that makes a tetrahedral, or that if we combine one s orbital with two p orbitals, that would be trigonal planar. Yeah, that would be trigonal planar. We're going the other direction. So we know that the tetrahedral has 4 bonded groups. So we know that we're going to have to hybridize 4 orbitals in order to make that shape. So an orbital diagram shows, so again, the idea here that we started off with was that hydrogen would have 1 electron in its 1s, and that we have these half-filled orbitals that come together. And when we take carbon unhybridized, would be, I guess not 1s, it would be 2s. And then 2p only has 2 half-filled orbitals, 4 total valence electrons. Once we hybridize those all together, now we've got 4 orbitals that are all equal energy level, and that gives us 4 half-filled orbitals. Okay. So our hybrid orbitals can accommodate a lone pair. So then because we have those 4, that's why we bond 4 electrons. Oh, this one is still sp3. Right, because if we were to do the Lewis structure for this, NH, we have a lone pair. So we have AX3E, that's 4 electron groups. So we're going to get 4 hybrid orbitals out of that. So the number of electron groups tells you how many orbitals you're hybridizing. And then if I was to do, all right, so this would be our sp3 hybrid orbitals. Nitrogen has 1, 2, 3, 4, 5 lone pairs, or 5 valence electrons. So filling that in, we get 3 half-filled orbitals that can go on to bond with 3 hydrogens, and one of those orbitals has a lone pair in it. So how many sp3 hybrid orbitals result from the hybridization of 1s and 3 p's? 4, quattro, yon. What's the Japanese? There's that 200 days of Duolingo paying off. Boku no namae wa Ringo desu. My name is Apple. All right, so yeah, the number of orbitals that go in here, the number of regular orbitals that goes in equals the number of hybrid orbitals that you get out. And that'll extend even into more orbitals. Now, when we're doing double bonds, get something a little bit different. So our regular bonds form from these hybrid orbitals. If we have leftover p orbitals, that's where our double bonds come from. So something with an sp3, we take an s, or sorry, did I say sp3? I meant sp2. We have an s orbital and then 2 p orbitals. They give us the trigonal planar. And then we still have, in this case, would be the PZ that's not hybridized. Yep. So for, this is formaldehyde. Right, so it's got the double bonded oxygen. We take this and we hybridize 3 orbitals together. So 3 orbitals means we have sp2. So that means that we get 3 half-filled hybridized orbitals, and we get 1 unhybridized p orbital. Now this oxygen, it has 2 unfilled orbitals. So it's going to want to form 2 bonds to fill in those orbitals, according to valence bond theory. And when we stick these together, the hydrogens will each take 1, and then the oxygen will take 1 of these hybridized orbitals, and those hybridized orbitals are all sigma bonds. So this is our sigma bond. And then the remaining unhybridized p orbital becomes a pi bond. Now those pi bonds, because they're off axis like this, and even when we draw them out as cartoons like this, they look really stretched out. They are weaker than the sigma bonds. So sigma bonds are head on, pi bonds are just like adjacent. And then, did we talk about it here? Yeah, I'll get to it in a second. So yeah, the half-filled py or pz, well, it could be either, forms our pi bond, whichever one is left over. Doesn't really matter. The sigma bonds are all overlapping end to end. And, oh no, it was here. So like the electron occupies both lobes, so the electrons are up here and down here. But this is the limitation of drawing things out like this and representing our electrons as these lines. We do that so we can see that they have coupled spins. One's upspin, the other one's downspin. But the electrons occupy both sides of this, and that's 1 bond. So now we're getting a little more into the stuff that we need to do tonight. So this kind of diagram, I think they're called flower models. So that's taking this from the Lewis structure, drawing out the carbon with its hybridized bonds, including the hydrogens, and showing the overlap of their orbitals, indicating that these are, the purple ones are all sp3, or sorry, sp2. The hydrogens are s, and then the oxygen is forming 1 bond with the sp2, and then another bond with the pi bond and the p orbitals. So just indicating where everything is attached. So valence bond theory and the way that we're going to use it gives us another layer on top of Lewis theory. Like I said, we've built all of these tools, and now we're going to use them all to get one more complete picture of what these atoms and molecules actually look like. So a double bond in the Lewis model always corresponds, that's not what I wanted. Double bond in the Lewis model always corresponds to 1 pi bond, 1 sigma bond and 1 pi bond in valence bond theory. So if you ever draw a Lewis structure that has a double bond, you're going to have a sigma bond and you're going to have a pi bond. And we haven't talked about triple bonds yet, but the trend continues there. And our pi bonds are generally weaker because there's just not as good overlap in those orbitals. So our single bonds, because they're just attached head on, they can rotate freely. And you get this effect too if you were to use like the toothpicks in those styrofoam balls that we used on Monday. Stick one in, you can rotate it freely. If you had something else attaching it, that would hold it and keep it from rotating freely. And that's what the pi bond does here. So since it's coupled at 2 points, we can't rotate them anymore. And so those double bonds actually fix the orientation of the atoms on either end. So in this case, the chlorine and chlorine are both on the same side. This won't rotate freely, so the chlorine and the hydrogen are able to swap places. On this molecule, these 3 can all spin. and rotate and change places. And they do. Crazy and free. So like here, these two are the same molecule because they're rotating freely. These are actually two different molecules, and we indicate the difference between them. Cis, meaning the same side. Trans, meaning opposite sides. Okay. A lot of words on the page. Test how awake you still are. In section 10.10, actually I think that's supposed to be 9.10, but we learned that double bonds are stronger and shorter than single bonds. For example, a carbon single bond has an average bond energy of 347 kilojoules, where a double bond has an average energy of 611 kilojoules. According to valence bond theory, why is a double bond not simply twice as strong? So it's a little bit less than twice as strong.
Yeah, it's gonna be A.
It is indeed A. So the sigma bond is stronger than the pi bond. So since pi bonds are weaker, it's not going to simply be double because we're not forming two sigma bonds. We're not forming two equivalent bonds. We have one strong bond and one weaker bond. The double bond, so the reason it's not B would suggest that if a double bond is just the sharing of two electron pairs, that would suggest that it should be twice as strong because we're sharing twice as many electrons. But that's not the case. And this is not an exception, despite the numerous exceptions that do exist. So triple bonds is kind of like the same thing that happened with double bonds, where we hybridize some orbitals, and then we've got leftover p orbitals that are sitting perpendicular to the single bond. And those can form bonds, those like side bonds. It's like the side hug of molecules. It's just side hug. So we can get two of those, though, going from two unhybridized p orbitals. So if you end up with something with two sp hybrid orbitals, and you have two unhybridized p orbitals, you can make, actually I think you will have triple bond. So looking at these sp hybrid orbitals, you get something that looks like a single p orbital by itself, but it's actually made up of two different ones, two different bonds. For this molecule, acetylene, we've got carbons and we've got hydrogens, and we hybridize in order to really, again for this class, we're hybridizing to make it work for this molecule, and based on the shape that it's going to have from Lewis structures from VSEPR theory. So Lewis structures, VSEPR theory, this is going to be carbon, and then a hydrogen, and then a hydrogen. How many electrons are involved in sigma bonds here, and just like head-on bonds? For one of the carbon. Just talking about this carbon for now.
The number of bonds in total?
Yeah, you can think about it as the number of bonding groups. For bonding groups?
Oh, the groups.
Yeah, 2. And so everything is going to have at least one sigma bond. So if you have a single bond, that's going to be a sigma bond. If you have a double bond, that's a sigma bond and then a pi bond. If you have a triple bond, that's a sigma bond and then 2 pi bonds. So for something like this, what I'm saying is, I guess what I'm trying to get at is that this middle one is a sigma bond and this is a sigma bond. And those sigma bonds, those head-on bonds, are going to be made up of hybridized orbitals. We can simplify that a little bit and say the number of electron groups total are going to be equal to our hybridized orbitals. So this has 2 bonds, no lone pairs, so that's 2 electron groups. Our valence orbital theory is going to say that we have sp hybridized bonds. So 2 electron groups, that means we take 2 of our regular orbitals and we merge them together to hybridize them. So it means we always take an s, and then we also bring a p along with it. And then for carbon, again, that lets us separate those 4 electrons into 4 separate orbitals instead of having any of them paired. And actually, I think I whizzed past this. Why are these electrons in the atomic orbitals of carbon, why are those paired instead of one of those just being in a p orbital? There's a piece of information that's missing from this image. What are the relative energies of 2s versus 2p?
Oh, 2p is more energy?
2p is more energy. So we're going to draw just these ones out. If energy is going up, then we'd have 2s, and then 2p would be somewhere above it in energy. So we fill in those two first, and then we put electrons in the 2p. So when we're hybridizing these, we're bringing the energy of the 2s up a bit, and we're bringing the energy of the 2p down a bit so that they're all the same. And once those energy levels are all the same, now the electrons will spread out into all of those orbitals. So that's why you can get 2 electrons in the sp, split up into 2 orbitals, and we still have 2 electrons left over, and they fill in the remaining 2p orbitals. So here, instead of just taking the whole 2p and moving it down, which would be sp3, we've taken our 2s, and we moved our 2s up a little bit, and we moved a 2p down. 2s, this is one of the 2p orbitals, and then the other 2p orbitals are still up here. This works because they don't hybridize like this by themselves. They're doing this when there are other electrons present, so that the hydrogens can fill into these, or the lone pairs can fill into. One of these would be from a hydrogen, one of these would be from a carbon, and the other two would form pi bonds. So we get these orbitals. The s and the p are these sigma bonds, and then the 2p are going to be the pi bonds made up there. So we look at a way better image of that than I could draw. So we've got our sigma bond that's through the middle here. Pick a different highlighter color or something. Sigma, oh, that's not better. Yeah, that's better. So we have a sigma bond through the middle there, and then a pi bond, and another pi bond. And remember, the pi bonds, even though like we show it on both sides, and we only draw the electrons in one of those sides, the electrons are in both sides, or can be in both sides. So this, you need a color that's going to show up on everything. This one and this one are the same pi bond. This one and this one are the same pi bond. And we can get there just from using our Lewis structure. All right, so what would the hybridization be of carbon and carbon dioxide?
SP2, right?
This will be our Lewis structure. How many electron groups are there for carbon?
8.
Electron groups.
Oh,
2.
Yeah, I was trying to.
So how many orbitals do we hybridize?
So then it
2.
would be SP.
So we always grab an S, and then we make up everything else with the P's until we run out of P's,
Then you go to
D's. When we run out of p orbitals, then we start using d orbitals, and we can hybridize further to get those more complex geometries that we saw. So here we get S, P, again, because 2 electron groups. And so we're going to skim past these real quick. I guess let's talk about one of them. Let's talk about this first, actually. So, like, your first step is always going to be to draw a Lewis structure. Then you're going to determine the number of electron groups. And then use the number of electron groups is the number of hybridized orbitals. Yeah, before we even move on to some of these other slides that we're supposed to look at, if I do I right, so this is I3 minus. And this is going to have 1, 2, 3. How many electron groups does I3 minus have? Or the central iodine in I3 minus?
5.
5.
So it'll be sp3d2.
Yes, but you're getting ahead of it. Yeah, so we've got 5 electron groups. So there's 1 s orbital, there's 3 p orbitals, and then we've got 10 or 5 d orbitals, not 10. So when we see 5 electron groups, we're going to take 1, 2, 3, 4, 5 orbitals, and those are the orbitals that are going to hybridize together to get it'd be a linear shape, but the trigonal bipyramidal shape that this is essentially. So this will be sp3d. And I think the one mistake that I remember doing while making these is forgetting to count the s. So like the mistake that I might have made here is I would do sp4d on accident. So they can't have 4 p orbitals. But for some reason in my mind, I wasn't counting them all up correctly. All right, but it's really just the number of individual orbitals that we take and lump together to create hybridized orbitals that all have the same energy. Okay, so that's this one, sp3d. And so all of those trigonal bipyramidal shapes, at least as far as we're going to go for this class, all have this same hybridization. Trigonal bipyramidal, if you take one of those off and you get the T shape, or 2 if you get the T shape, 1 you get the seesaw, those are all sp3d. And so if we incorporated another group, that would be the octahedral. And so we just take another d orbital and combine it in there. So it's sp3d2. So this is the part that we need to get to. It's bonding schemes. So how do we know which hybridization scheme best describes the orbitals of a specific atom and a specific molecule? The rigorous way to do it would be degree and type of hybridization. You calculate to give the best model with the overall lowest energy. That's quantum physics. We're not going to do it. I won't stand for it. Instead, we're going to use the method where we assign a hybridization scheme from the electron geometry of the interior atoms. So counting up those electron groups is just going to tell us how many hybridized orbitals we should have. And if you really even wanted to, you could list these out. So the smallest number we'd have was 2 electron groups. So what would our hybridized orbitals be? sp. If we have 2 electron groups, I said, wow. On fire this week. sp2. 4 electron groups. I can count, I swear. sp3. 5 electron groups. sp3. Remember, we only have 3 p orbitals, so we have to use a d orbital now. And 6 electron groups. Yes. Now, if only they had named some of these R, and then we could get R2D2.
Or switch the P and S, PlayStation 2.
Yeah. PS2.
3DS.
Or Nintendo 3DS. Okay, so that really boils it all down. And then your hybridization schemes. And these, again, go back to those core geometries that I was telling you about from VSEPR Theory. And then you're swapping out, since they're all electron groups, you can swap those electron or the bonding pairs out for lone pairs and get different geometries. That's another table from the book. Should be 10.3? I think it should be 10.3. Okay, so bonding schemes, we're going to try our best to be neat about bonding schemes because it can get messy in a hurry. So we're going to write the Lewis structure for the molecule. I mentioned use VSEPR theory to predict the electron geometry. Then select the correct hybridization for that interior atom. based on the electron geometry, like we talked about, sp, sp2, sp3, sp3d, sp3d2. Those are your options. And then sketch the molecule beginning with the interior atom and its orbitals. Show overlap with appropriate orbitals on the terminal atoms. Label all bonds using pi or sigma notation, followed by the overlapping orbitals. I know it sounds like a lot. Let's do an example. And actually, I think I'm going to modify this method a little bit, just a teensy bit. Okay, so what's the first step? Lewis structure. Wait, I don't know, I drew it over there. XE. Right, Lewis structure. We can skip some steps here, right? We can count up all the electrons. We can distribute those electrons. We can find out that there are more electrons than we can fit on just the fluorine atoms, and we can decide to put those electrons on the central atom. Skip some steps. Okay, so what's the next step?
Establish electronic geometry.
Yeah, establish electronic geometry and electron groups. Right, so to establish the electron geometry, we need to know how many electron groups we have. So how many electron groups do we have? 6. So what's the correct hybridization? Yep. And you can do this, right? So I know I have to get to 6. So if I start with S, that's 1, and then P, and I know if I add 3 p orbitals, that's only going to get me to 4 total. And then I'm going to need 2 more, so we grab 2 Ds, right? So they'll add up to that total. sp3d2. I wrote a 4, huh? Okay, now, do we have any double bonds? Nope. All of these orbitals, right, there's going to be one that's going to have these. They're all going to be sp3d2 hybrid orbitals. And so I'm actually going to rewrite, I don't know why I'm doing this on this book. So I'm going to write a xenon, and then I know that I'm going to have fluorine and fluorine. And instead of drawing the orbitals in first, I'm going to suggest that you put a line in between each of these. That's going to represent the electrons that are forming the sigma bonds. And the reason I think you should do this is it'll help you draw your orbitals large enough that you can write legibly inside of them. Because we're going to write the things that go in the orbitals first. So how many electrons are going to go into each of these? Yep. Okay, and those are all sp3d2 hybrid orbitals. And then we're also going to have, this is not going to work great for this, but we need to put the other 2 electrons in here for the lone pairs. This is a flower diagram. Wait. I'm getting ahead of myself, huh? No. Yeah, because we're going to have to draw flower. Sorry, these are called flower diagrams. I don't have it written in the slide. Flower diagram. So then, honestly, we can label all of the xenon to fluorine. So this is going to be, so this from the xenon is an sp3d2 to which on the fluorine? Well, it's not going to be hybridized on the fluorine.
We're talking about what kind? Would it be a
P orbital. It wouldn't be a sigma. So hydrogen does the sigma. Hydrogen does the sigma because that's all it has. But the p orbital is going to stick out farther. And so it's going to be more in a position to overlap with the xenon. You can even just draw, so all of the fluorine xenon bonds are that. And then this is, I mean, these are not bonding.
So based off the flower diagram, we determine what orbitals F is in fluorine?
Oh, I did these, hold on. That's how you're supposed to do the overlap. So there's supposed to be one orbital coming off the xenon, one orbital coming off of the fluorine so that they cross. These are just pretty inherently messy. So if you have anything, really if it's anything that's not hydrogen, it's going to be a p orbital that's going to be bonding.
What if it's like hydrogen's going to be like an S?
For hydrogen, it would just be its s orbital, because that's all it has. It doesn't have more than one electron. So it doesn't have any electrons in p orbitals. The valence electrons in fluorine are going to be in p orbitals. Kind of wish we had started with this one. Okay, so hydrogen cyanide, Lewis structure. So what is the hybridization on, or how many electron groups does carbon have?
32.
Yep. 2 electron groups. So what are our hybrid orbitals? Just sp. So then for the flower diagram, so it's 2 electron groups, which means it's sp. So each of the sigma bonds, oh, that's what I didn't label as the sigma bonds, but those are other ones for sigma bonds. So these are going to be our sigma bonds directly in between. So those are the orbitals overlapping with the electrons inside. And this one is going to be, actually, I should ask, what is that one going to be? So we got hydrogen something bonded to carbon something. Which orbital from the hydrogen is bonding? S. And what is it from carbon?
That would be, or no, this is still S.
No?
Is it D?
¿Por qué no los dos? Why not both? It's sp.
Of course.
So that's the hybrid orbital.
Right.
So on the other side, the carbon-nitrogen bond. What is the bonding orbital from carbon? sp. And then from nitrogen?
Is it a P?
Yes. It's a P. And then, how do we represent the triple bond?
Oh, 2 pi.
2 pi bonds. Yeah, so it's 2 pi and 1 sigma. So we got the 1 sigma bond. And actually, we should write that this is a sigma. This one's a sigma. Then the pi bond, these things get just so messy. I'm gonna draw one up there, and then imagine an axis like this. There's gonna be another one that's out here. So those are connected, and that these are connected, so we can put an electron in there, an electron in here, and then this is gonna go and do one of these numbers. Then this is going to come out here and get this guy. This is going to come out here and get this guy. And then there's also ones on the other side.
Oh,
There's got to be a better way.
I know what you're trying to draw, but it just doesn't.
It's bad.
It just
No, what is this? I could have just scribbled on the page and said, this is what it should look like.
Actually,
3D model. Trying to 3D model.
3 bars going across is fine and all, but like we need to indicate that this is a pi bond and that it's carbon to nitrogen. Now, what are these bonding orbitals here? What's the bonding orbital from carbon now? It's not S? You can probably pretty safely say, unless it's part of a hybrid. Like the hybrid orbitals, S will always be involved in hybrid orbitals. Unless it's hydrogen, nothing else bonds with sigma bonds. So it's not sp. We had 2 sp bonds. We used one for the sigma bond on hydrogen and one for the sigma bond on nitrogen. So we have some unhybridized orbitals.
Just a P by itself.
And what about the nitrogen? Also P. That's a pi bond. And then this one is going to be carbon what to nitrogen what?
I'm guessing both of them are
P. And that's also a pi bond. Okay, that's all we're going to do for flower diagrams because we got to talk about molecular orbital theory. And for molecular orbital theory, we're going to keep it fairly simple because to make it complicated makes it really complicated. Schrodinger's equation for even a simple molecule is impossible. So instead, use trial functions. So you pick a function as an educated guess to best map it. So then computers are used to calculate the energy of the trial function using the Schrodinger equation, and then it's optimized for the lowest energy. So you're giving it somewhere to start from and then saying optimize from there, and then it'll try and make it better. And then you modify your trial function and say optimize from this starting point. We're not going to do that. So what we do instead is le cow. I was going to look up a picture of a fancy French cow and put it in here to make you guys remember that it's le cow, LCAO. Linear combination of atomic orbitals. So here we're stepping things up a notch a little bit, and where valence bond theory hybrid orbitals only combine orbitals of a single atom, many LCAOs, LCAOs, are delocalized over the entire molecule. We're going to be looking at a little bit more complicated stuff. So for hydrogen, one of the molecular orbitals is an equally weighted sum of the 1s orbital from each atom, which is the sigma bond for the shape. It's a bonding orbital because the energy is lower than the orbitals it was bonded from. Wow, that's fun. That is so purple. Yes, it is pink. It's fuchsia. So lower than the energy it was formed from. So we get a lower energy, that's a bonding orbital. So that's a favorable interaction. We can't have unfavorable interactions. So the next molecular orbital for hydrogen is made by summing up the 1s orbital on the one atom with the negative or opposite phase of the 1s orbital on the other atom. So it's subtracting. So on the one hand, we have those orbitals that are interacting or they're really interacting. They're interacting positively, so it lowers the energy. On the other side, you get destructive interference. So remember, electrons have wave-like properties. And with waves, we can get constructive interference, destructive interference. When they're bonding, we get constructive interference. When they're anti-bonding, we have higher energy, so it's resisting the bond, it's destructive interference. So those are the anti-bonding orbitals. I need the highlighter. There we go. So we can combine these together, and then depending on how many electrons each atom is bringing to the bonding or anti-bonding orbitals, we can determine if something is going to form a bond or if it's going to form multiple bonds. For hydrogen, we can map this out like this. So you've got one hydrogen atom and another hydrogen atom, each of them bringing one electron, and each of them bringing one with opposite spins. And under the best circumstances, they'll have a bonding interaction, and that's the lowest energy place where those electrons can interact. And then if there are more electrons, then they enter this anti-bonding state and reduce the amount of bonding energy. So for hydrogens, this ends up being favorable because each one brings one electron, they bond and form a sigma bond, and there aren't any electrons left over that would go into this anti-bonding orbital. So it's only constructive. And we can use this to determine the bond order. So for bond order, we add up the bonding molecular orbitals, the number of electrons in the bonding molecular orbitals, subtract the anti-bonding, divide by 2. Because 2 electrons makes 1 bond. So if it's a positive number, then you form a bond, and you can get higher order bonds this way. The higher the bond order, the stronger the bond. And then if your bond order is 0 or negative, then you don't form a bond. And that's what this worksheet is. Oh, yeah, the first one was in class. Let's skip the first one for now. So on your worksheet, draw on the electrons and predict the bond order for the following molecules. Find the number of valence electrons in the atomic orbitals and place them on the unbonded orbitals, or unbonded atoms on each side. Then mix, create molecular orbitals, and fill in all the valence electrons according to the Aufbau principle, lowest energy to highest energy. And that's what I got here. Actually, maybe we should just switch to so here's the worksheet. So how many valence electrons in bonding orbitals does helium have? How many valence electrons? 2. So each of these is bringing 2. And so what we're representing here is that these are where those electrons come together and combine. So we got to take all of these, we got to use all of the electrons that both of these are bringing together and fill in until we run out of electrons. Oh. Sorry. Yeah, this is helium. This is helium plus.
You've done the bond orbitals first, and then?
So you start at the bottom and fill to the top.
Okay.
So we got 3 electrons total. We'll go 1, 2, 3. So how many bonding electrons do we have? 2. So this will be bonding electrons minus anti-bonding. How many anti-bonding? Sigma. Just 1. So this will equal, so then we got to divide by 2. So that'll be 1 divided by 2. So our bond order is a half. So it's not that a bond wouldn't form, it's just not going to be very favorable. If it does form, weak at best. And that's assuming you get helium plus. So for the second one, if we go 1, 2, 3, 4, because we have 4 electrons, how many bonding electrons do we have? 2. Subtract anti-bonding, which is how many? 2. That's 0. And we divide by 2, and that's still 0. So no bond.
Actually, that's undefined. Is it unity or is it?
They know if it's divided by 0.
0 divided by 2, okay. 2 divided by 0 doesn't work. going to take my pizza and I'm going to divide it into 0 slices. Now I have infinite pizza. Let's see. Okay, the thing that you need to know is for these simpler, what are they called? Homonuclear diatomic molecules. For really simple stuff, I think it's really just hydrogen, helium, lithium, and beryllium. It's going to be this. So this same structure. You're going to have antibonding, you're going to have bonding. Once you get to the period 2, more complicated stuff, there's a thing that can happen, and actually I should probably switch back to this. Okay. Yeah, period 2 homonuclear diatomic molecules. I'll give you the structures for these, you just need to know how to fill them in. By the structures, the molecular orbital diagrams. So a mnemonic you could use, if you needed to know this, is be careful now. Because what happens is the way that the atoms interact to form bonds lowers the energy of the 2 pi orbital and increases the energy of the pi bonding 2p orbital. So these are, the expected order would be this, that the sigma would be lower, so it goes sigma, pi star, sigma star. So sigma star is the antibonding, pi star antibonding, star is the antibonding. This is the expected order, but the actual order ends up being this. Now if I gave you this, I just want you to know how to fill this in. So if, for example, we'll just do it on here. Let's do carbon. So we've got a carbon over here, and we want to fill in the valence electrons for each of these on their respective sides. So how would I fill in the valence electrons for carbon? One, two.
There's 2 tops on the T.
2 in the P.
Right side.
And then the same over here because that's what homonuclear means. 2 of the same nuclei, 2 of the same atom. Okay, so now our sigma bonds or sigma electrons, 2 s electrons, 1, 2, 3, 4. And then for the 2p, 1, 2, 3, 4. So it's actually the 2p orbital that's forming that bond. Because the sigma and the sigma star cancel each other out. Because we could do it like this too. Let's do the whole, how many bonding electrons do we have? To figure out bond order. 6. How many antibonding? So minus 2 divided by 2 equals 2. So we'd expect that to have double bond. So it's boron, carbon, and nitrogen that have this unexpected order. Oxygen, fluorine, and neon would have the expected order. So the sigma is always lower than pi. And the separation between the pi's is actually smaller than the separation between the sigma bonds.